Okay, guys, welcome to Ice Education, the only education that matters. My name is Ice Tachi. Today we'll be doing vibration of coupled pendulum with a spring. So, yeah, example 2 from the PDF given by the lecturer. Can you guys see my screen? Please give me a feedback. We'll be dealing with example 2 just right now. So, what is example 2? Let me just open the PDF and see what's happening. I hope I share the screen. Let me just check before. Yeah, my screen is shared. So please feel free to ask question. If you don't understand something, please ask your question. Okay, example 2, as stated, they said a machine part consists of 3 levers connected by a lightweight linkage. Lightweight linkages. A vibration model of this part is shown in figure 3. Use the Lagrange's method to obtain the equation of vibration. Take the angle to be the general's coordinate. You can see that information. Take the angle to be the general's coordinate. Linearize the result and then put it in matrix forms. So this is what's going to happen. In this example, we are not going to linearize it. We're going to solve it as it is. And then we're going to linearize it after. If you remember on the previous example, what is linearization? Linearization is simply you have relation between angular and linear motion. For instance, we know that if you have x is equal to r theta. This is the relation that links linear to rotational. This relation comes from a circle. If you guys remember in mathematics 1, where you guys did something like this, you have a certain displacement, you guys call it s, and this angle was theta. I think we call it arc of a circle, something like this. If you want to solve the displacement s, it is simply r theta. So this s here, it's simply standing for x here. So what is the relation between the two? It simply means in such system you can write it in two ways. You can have it in linearization form. When they say linearization form, it simply means everything should be in terms of x. That's what it means. This is what they mean by linearizing something. It's simply writing everything in terms of x. So from this relation, you also have another one. You have x dot, it is equal to r theta dot. And you have x dot dot, which is equal to r theta dot dot. So what is the trick, guys? It's very simple. If I ask you to write something by linearization, it simply means you can solve your question the way it is. If it is with theta, you solve it with theta. If it is with x, you solve with x. I know it looks a bit like, how can I say it? A lot of theory, you don't see what's happening, but as we move, you will see what I'm talking about. If you write your equation in terms of theta only, it means at the end of your equation, remember this relation. If you want it to be in terms of x, what does it mean? You express it in terms of x. Let's say you write your equation in terms of theta, you have theta dot, theta everywhere, and they want you to linearize it. What does it mean? It simply means, if I come to this relation here, I want everything to be linearized. I only make theta dot dot subject of the formula. In that case, theta dot dot will be x dot dot over r. Therefore, I have linearized my solution. That is what they mean. So it simply means, if your system is angular, you solve it as angular. At the end of the day, then you can linearize it. But you will see as we do it. But this example here, we're gonna solve it as angular and then we'll linearize after. So it's just a quick explanation. Let's look at the system and then we can do it together just right now. Please, if you have a question, feel free to raise your hand or speak, and this video will be recorded and I will do my best to edit it and put on my YouTube channel so that you can go to it a couple of times, and if you still have question, you can ask me for clarifying. This is what's happening. We have a vibration system consisting of 3 pendulum. I'm pretty sure you guys have seen the pendulum. For those who have seen old watches, if you've watched Stranger Things, there is a watch on season 4 or something like that. But if you haven't watched it, in back in the days, in old, can I say old time, something like that. Back in the days, watches used to be something that has weight like this. Every second, it swings like this or like this. It goes up, down, as time is moving. This is an example of a pendulum. This is basically what we are studying here in this example. But now, in this example, we are having 3 pendulums coupled together with the help of springs. That's what's happening here. This line here, it shows that the spring was first horizontally, and due to a certain time, it has expanded to it has moved to okay, as time moved, the pendulum moved, it created an angle of θ1. This is what's happening here. But now there is something important to notice. With this spring here, we have relation attached to springs. That one is spring 1. This one here is pendulum 2. Let me write it like this. I know my drawing is not as accurate, but you guys have the PDF. You can see what's happening there on the PDF. But it will look nicer as I solve. You will see, and you have another spring coming like this, and then pendulum. Sorry, I know it doesn't look nice the way it is here, but it will be fine. This is θ3. Okay, here this is what we have. If you guys remember on the previous session, I said on the previous session, sorry, I've opened this one. Where am I? If you guys remember on the previous session, I have said Lagrange's formula is quite easy. You only need to know your variable. If you have a rotating object or you have a masses, and I said you have 2 types of energy that you need here. The kinetic energy, the one that we call chi, which is half mass x dot square, velocity square, or half moment of inertia, I, theta dot square. And I said this one is for linear motion, this one is for angular motion. And I even said that time that if you have a mass of m, let's say you have an object m, and you want to find its kinetic energy, therefore that mass goes with this formula. What is the reason with that? This mass that we see here is only having one motion, one direction of motion. It's going in the linear form, like this or like this. That's the reason why it goes with this one. But if I have an object attached, you can see there is a weight impacting here. Use a weight. This object here, it is not having a linear motion. It simply means if I swing the object, in this case, because it is being swung, it's created an angle. Therefore, this mass that we see here is now a rotating object. Because it is a rotating object, therefore it has a moment of inertia. Is it making sense, guys? Now, that's just a quick recap as we move. Who's joining now? Peter, okay, doesn't matter. Now, what is next? This is the type of kinetic energy that you have. You also have potential energy, and in this chapter, you have 2 potential energy. Mostly, in 100% of the case that you have, one is due to the spring, which is, we know it is, the formula is half k x square. This is the potential energy due to the spring. And you have the potential energy due to the weight, if only that weight is having a swinging motion, is vertically and then it moves as a rotational object. I don't know if I'm making sense. The object is here, it started here. As you move it, it is somewhere here. Due to that, because there is a change of height, it was here, now is here, there's a change of height. Because of that, it has what we call potential energy. And what is the potential energy due to height? What is the formula about it? It is simply mass of the object multiplied by the gravity and then height. The height created. What is the height? Because remember that object had an initial position and it also have here a final position. Due to that, if at initial it was here and finally somewhere here, there is a height created. This is the height that we are talking about. So guys, believe me, if you have a vibration problem and you have to solve it using Lagrange's, if you get your kinetic energy right, your potential energy right, you will never ever fail this type of question. That is the reason why I'm starting with this one. So in this our case, now let's study the system together and then we solve it. This class gonna be a bit long. It's gonna be maybe 2 hours and a half because I want to finish it today. But as I'm moving, I also want to explain so that we can be on the same page. So far, please, are you confused anywhere or you don't see what I'm doing? If you don't see, don't worry. As we solve, you will see when we get practical how it is done. This is just a theory along it. But please ask your question. I would like to erase it and then we can solve this problem. Hey, Mr. Bubakar. Welcome, my brother. Now, here we go. What we have to study here, we study our system. In this system, how having a linear or angular motion. As we can see, the way it is even shows, they gave you theta 1, theta 2, theta 3. It simply means in this case, you are having angular motion. And if you are having angular motion, it means the type of kinetic energy that you'll be having should be angular kinetic energy. Here we go. I have mass 1, this is 1, this is 2, and this is 3. It is swinging. Because it is swinging, it is having a kinetic energy due to angular motion. So if I have to write this expression of kinetic energy, remember Lagrange is all about kinetic and potential energy. And this is the general formula of Lagrange's. Let me just write it down on the side so that you can see what's happening. It says the general formula say it is d in term of g of partial g partial q dot, this means it's velocity qi, like this, minus partial g over partial qi, like this, plus partial u over partial q, something like this, to be equal to 0. Now this is qi. This is the general formula of Lagrange's. But how is it done? So far you can see it's all about, you can see by the formula, it's all about kinetic and potential. So first thing to do, you determine your kinetic and potential energy in the system that is given to you. So in this case, if I have to get the kinetic energy chi, because this thing is rotating through an angle, therefore I will be having it as half moment of inertia. Now theta 1 dot square, this is the first one for object 1, plus second here it is half high, let me call this one I1, moment of inertia 1, moment of inertia 2, theta dot 2 square, plus half moment of inertia 3, the way it is here, theta dot square 3, you can see here. I don't want this one to confuse anyone, this dot here, not part here. Yeah, now we have written the kinetic energy for this system. That's how it is done, simple as that. Now, what is the next step? It is moment of inertia. If you remember from theory of machines in diploma, we knew that each and every object has its moment of inertia. We have what we call a disk. If this is a disk, if I remember well, moment of inertia of a disk, it is simply half m r square. If you guys remember well, we have for a disk, we have for, let's say, which shape again do we usually know? A bar. It was like this for a bar, 1 over 12 ml square. This is the moment of inertia when it passes through its axis of rotation. If you guys still remember it, but these have been covered in earliest classes in diploma. But don't worry, they will not ask you about this shape here. You won't be having them here, just for you to remember. The reason why I'm saying this is because sorry, when you have an object, a mass that is shapeless, we call it concentrated mass. So for the moment of inertia of a concentrated mass, we call it concentrated mass because it does not have a shape. We don't know if it is a disc, a bar, or what. We can't find it. So usually in such case, let me just add this person. Oh, Tokozile Cynthia. Welcome, Tokozile Cynthia. Okay, guys, because we don't know the shape of this object, how do we solve moment of inertia of this object? We call it moment of inertia of concentrated mass. It is simply the mass of this object multiplied by the distance where the object is to the axis of rotation square. Let's say for instance I have a block of mass here and it is pivoting through an axis here like this. Let me write it like this. It's gonna be swinging through, let's say this thing is creating the angle. If I want to get the moment of inertia of this shape, it is simply the mass of this multiplied by the distance where the object is to the axis of rotation. Let's say the pivot here is center or origin and the distance here it is x. Therefore, moment of inertia in this case is going to be mx square. Now let's come back in our case. Because this is our concentrated mass and the distance of the mass to the pivot, remember the pivot point, it is simply the point at which we have the motion going on. We call it pivot point. So the distance from the mass to the pivot point, they called it L. Reason being, if I want to rewrite this moment of inertia here, it is simply going to be half. What is moment of inertia of object 1? It is mass 1, which I can call m1, multiplied by the distance of the object to the pivot square. What is that distance? L. So therefore L square theta dot square. That is the reason why when I sent the PDF you saw m1 and L. We simply got the moment of inertia of this mass here that we call concentrated mass. It is a concentrated mass because we do not know the form of it, if it is a disc or a bar or whatever, because we have moment of inertia of different shape type of object. So you can just look on it, but if I have time, for sure there will be a video in theory of machine that I will come back to these basics, but that would be on my YouTube channel. Now here we go. You are given K1 and you are given K2. We call it spring constant. Now let's write first all the moment of inertia here. I'm erasing. Now what's happening here, guys? What's happening is I'm gonna be half. I'm gonna do the same thing for the second object. Remember, if you look at the picture, the problem given by the lecturer, the distance L is the same for all the 3 springs. It is the same, as you can see from that picture there. So it simply means if I have to rewrite the kinetic energy for this one here, it is simply half. The only difference, this one I will call it m2, the distance where mass 2 is to the pivot, which is still L. m2 L square theta dot square of 2 plus, same thing with object 3, half m3 L square theta dot square of 3. Now you are done with the kinetic energy of this system. It is very easy, guys. Any question? Are we good? Now I want you to pay attention. We have what we call potential energy. You have two potential energy due to the weight and due to the spring. We have potential due to the weight because the weight is swinging. It has the initial position and it moves to another position. I have explained it earlier. The weight is like this, it is here. As it moves to somewhere here, because of this change of height created h, therefore we have what we call the potential energy. But let's write first all the potential energy due to the spring. Now here we go. Do we all believe that at the beginning we have a system like this? You have spring, and then you have another mass, and then you have spring like this and another mass before being stretched at a certain angle. We all believe that. Now what's happening here? As we can see now, the angles are created. If we have to write the potential energy here, U, in this case, if I have to write the potential energy U here, I'm going to have, okay, before I write even the equation, this needs to be explained, guys. If my object is here before being stretched, the spring, it means the spring is somewhere here, is still, do we call it stiff? The string has not been elongated. It has an initial position. Now, do you agree? As I move this, let's say I move this is the spring. Do you agree that the spring constant, remember the spring constant, we say it is half kx square. The spring constant created, it is simply the distance between the initial position of this chord here of pendulum to the final position. That is one of the reasons why I called it R on my PDF that I shared with you. Now this is R, but remember this spring one in this case, it is also attached to another object here. Remember, another object here. You can see the way I'm analyzing theta 2 here. Now it also created what we call what here, R2. I'm analyzing it step by step. I'm analyzing it only with the first two spring first. In this case, because my spring K1, it is between object 1 and object 2, therefore there have to be a change in elongation. Now you have the freedom in your change of elongation, but now you stick to what you choose. You can take it as R1 minus R2 or R2 minus R1. You still gonna get the same outcome. But what I mean is, the order that you choose, you keep it until the end of your solution. But now for preferences, for the way I like doing it, I always like taking final minus initial. By that I mean, in this case, the potential that I'll be having here, in this case, where's my mouse? I'm going to have half K1. Because the spring K1, it is between R2 and R1, I will be writing it as R2 minus R1 everything square. Any question, guys? This for spring 1. Now I will do the same for spring 2. Spring 2 is between what? Yeah, someone asked a question. I think that's a question. Is it a question? Mr. Kumalo.
Yes, I have a question.
Yes,
For the potential energy, don't we include the mass?
yeah, I will add them.
Oh, okay.
I'm writing first for all the springs.
Okay.
Yeah, thank you, my boss.
Thanks.
No, you're welcome, my brother. Now, I have spring 2. Spring 2, it is between object 2 and 3. So in that case, I'm going to be having plus half K2. Now, I will go R3 minus R2 square. Remember, I insisted here, the order that you take is the order that you keep. If I started with R1 minus R2 square, it means in the following one, I will also start with R2 minus R3 square. I don't know if you get what I'm trying to say. If you come on the second one, you said R3 minus R2, you are changing the order. Now, when I said R1 minus R2, it means I am doing initial minus final. It means I keep it like this throughout my solution. I do not change anything. It's either you keep initial minus final or final minus initial. The choice is yours, but one thing is sure, you will get the same outcome. But do not mix both of them in a solution. It means you will get it wrong. If you decided in your mind you want to go final minus initial, you keep that order until the end of your solution. Please do not mix them. It is really important, and I believe you guys are getting what I'm trying to say. If you don't get it, please, you can ask me. Now, here we go. We are done with our springs. Now, we move to the masses, the object mass. Now, if you remember, I'm pretty sure you guys have seen this in Physics 1. This is object of mass, M. Are we agreeing? As this is swinging through a certain... Remember, this is L. This is also L. It is just swinging. You guys can see when something is rotating. If you have a circle, this one is R. This one is R, the radius. When it comes here, it is still R. This is what's happening in this case. But now, when do we have the potential energy here? We have potential because there is a difference in height. It means your object, when it is here, it is at initial position. There is no height created. But let me put it like this. As it has moved to a certain distance here, now there is a height created. Now this is the weight of the object, mg, if you guys remember from Physics 1. Now and we have this difference in height here. Remember, we have called this height here to be h. Is the same thing. We have called this to be h. Now, because there is a difference in height, we have the potential energy of this object mass. How do we write it? Potential energy of this object, it is simply mjh. But now, as we remember in Physics 1, what we usually do, we express h in terms of L. How do we do it? Look what's happening. I'm going to use a different color. This one is an angle theta. Do you guys agree that this distance here, if I want to get this distance here, as you see here, remember, I want to have something that I call like a right angle triangle, so that I can use my cos and sec. This distance here, remember, L is a distance. Remember, from here to here, it is my L. But if I have something coming here, I have h, right? And I need to get this distance on top here. This distance here, it is simply full length L minus height. I don't know if you guys see it. Do you see it, my guys? I feel like I'm not explaining this well, this part of L minus height. Okay, for instance, yeah, this one will make sense. If everything here, from here to here, it is 4, and you have, let's say, something here, a small particle of 2, let's say 1, and what you need, you only need these distances here that you see here. How do you get this distance? It is simply total length 4 minus 1, which is what? 3. So in that case, 3 is this distance here. I don't know if you see what I'm trying to say. Who wants to join here? Someone wants to join. Who is this? My brother. View ad. Nah, it doesn't want me to hide you, my brother. You are late. You will watch on YouTube. Yeah. Sorry. Let me erase and start again explaining this thing. I want you to get it. Guys, let's move. Okay. we have an object swinging like this. This is still L. I don't know if you guys see it. This is still L, but at a certain angle theta. This is L before swinging. Now this is creating a difference of height that we call H. Now I know that my potential energy is equal to mgh, but what I want to do is to express H in terms of L. How do we do it? If this is H and this is L, what is this height here? It is simply full distance L minus H. In this case, what do we do? Now that we have what we call a right angle triangle, something like this, where you have L minus H on your cosine side and you have L as hypotenuse. Now, what do? You go with cos theta, which is what? Adjacent side, which is L minus H over hypotenuse L. Now, what do? You want to express H in terms of L, so you cross multiply. You're gonna be having L cos theta to be equal to L minus H. Now, if you want to express H as subject of the formula, therefore you will be having L minus L cos theta. And guys, remember, in your solution you do not have to prove this. I'm proving this from my explanation. So what does it mean? H, you can make L as subject of the formula. It's going to be L1 minus cos theta. If you look at the PDF that I've sent to you in the group before, this is the expression that I wrote down. This is where it comes from. So in this case, what will be the formula of potential energy? It's going to be mg. Now what is H? H will be L1 minus cos theta. Now only what you have to remember, it is this formula here. When you have a pendulum swinging or a mass swinging at an angle, you know that my H will be L minus 1 minus quarter 1 s y o minus quarter, what am I saying, minus cos theta. This is what you need to remember, but I was just showing you how we got to this point. It's better to know what we are doing. Now for instance, now I have discovered it, so what is next to do? Who wants to join? Sorry guys, someone wants to join. My guy, I'm trying to add you here, but it doesn't want me to add you, fortunately. Unfortunately, this now since we got it, guys, let me erase. Since we know what we are expecting now in the solution, it becomes easier, guys. I'm taking time, and you will see the rest that will follow is just math, straightforward. But what is important at this equation? So I'm dealing with object 1, mass 1. So my potential due to mass 1 is going to be m1 g, gravity, and then I'll be having L1 minus cos theta 1. Easy, you just copy now and paste. Second mass is what? m2 plus m2, you have g L1 minus cos theta 2. Do we have another expression? Yeah, we have m3. Let me just write it down here. I know it doesn't look nice and neat, but yeah, let me just write it here. It's going to be m3 g L1 minus cos theta 3. Now we have written our kinetic and potential energy, but now there is something that I'm not satisfied with. You can see here everything from the kinetic here is in terms of theta, from the potential on this side is in terms of theta. I am not satisfied with this r here and this r here. Now therefore I have explained this earlier, if you remember, but I'm explaining again now. I want to transform this r here in terms of theta, so that I know now I'll be having all my function in terms of theta. Is gonna be easier for me to work on. Now for that, should I on zoom first? Yeah, let me zoom and pen. Now, here we go. Let me use the black marker. I want to explain the R. These are where they are coming from. Remember, I've showed you something that we did in Math 1. If you have a circle starting a point here, as it swings to a certain distance, it creates an arc of a circle. It creates a distance that we call S, and I said S is equal to the radius times theta. Now, what is happening here? The R that I'm calling here, please do not confuse it. The R that I'm calling here, it is simply the distance created by this change here. It is my S, like in this case here. This is the R that I'm talking about here. So when I said R2 here, R2, it is simply R2, it is simply in this case R2. Remember this formula here, when we said S is equal to R theta, the R that we are talking about here, because the circle is here, this is the center of a circle. The distance from here to here, it is the radius of the circle. As it swings to a distance here, let's say created an angle theta, this S, we said it is R theta. The R here is tending as what? Radius. In this our case, this R here, it is simply the length L, which is acting like a radius. That is the reason why for R2 I will be having L theta 2, and for R1 I will be having L theta 1, and for R3 I will be having L theta 3. Now, if we want to write everything now in terms of our theta, yeah, ask a question.
Sorry, Mr. Iceman. Can you repeat, please? I'm just a bit lost.
Or you are just a bit lost.
Yeah, on the R2 and on the radius.
Or on the radiuses.
Yes.
Okay, I would like to explain something, my brother. I call this R, but remember, this is a thing that where it was a bit confusing, but let me just explain it, my brother. When we have a spring stretches through a certain distance x. That is the reason why we say potential of the spring, it is half kx square. In this example that we are doing here, I simply call this x to be R. I think that's what we should get first before I move further. This is the elongation of a spring that I have called R, but it's supposed to be X. Now, my brother, do you agree that if we have a circle, this is our center point. From here to here, I have a radius. As I move to a certain distance along my circle, I create an angle theta. Because I have created an angle theta, I call a distance that we call arc of circle. That's what we call in mathematics 1. We call this S in Math 1. If you want to find out what is S, it is simply your radius multiplied by what? The angle that is being created. Now, how does this being related to what we are doing? We have a pendulum of mass here. It means, what is this distance for us, Mr. Bubaka? It is L. Now, our pendulum has shifted through a certain angle. I don't know what's the angle. Let's say theta 1. Now, remember the R that we're talking about, the spring displacement. It is simply the distance covered by this pendulum. That's the one that we called R. In this case, if you want to solve R here, it is simply going to be L multiplied by theta. L here is tending as this radius here. So now, that's what I'm saying. For each and every displacement of this case here, let's say for object 1, if I want to write for object 1, R1 here, if I want to write it in terms of L and theta, it's simply going to be L multiplied by theta 1. For object 2, it's simply going to be L multiplied by theta 2. For object 3, it's simply going to be L multiplied by theta 3. The reason why L is the same here, it is because in this case, it is the same object being displaced through the same, you can see by the picture, it is seated at the same length and same displacement of angle. That is the reason why I'm not saying L1, L2, L3. I'm writing L because they are all having the same distance L. Is it fine, Mr. Bubaka?
Yes, yes, it's fine.
Yeah. Now, if we get this one, my brothers and sisters, we can rewrite our potential energy equation. We can rewrite it now in terms of L and theta. So in that case, our U2, no, why am I saying U2? Our U, and you can see, guys, I'm spending time on potential and kinetic because this is what you need to understand. Otherwise, the rest is very easy. You have half K1. Now, where I have R2, I simply replace by L theta 2 minus L theta 1. Everything square. Same thing, plus half. When I have, now I have K2. Where I have R3, I replace by L theta 3. Where I have K2, I replace by L theta 2. Now we move, let me erase here for space and neatness. I erased that one. What happened there? Anyway, it's fine. I'll rewrite it. I'm rewriting it anyway. Let me pen again here. Yeah. Now I come back with my masses. My masses here, it is M1 GL1 minus cos theta 1 plus M2 G. Hey, this time will kill me, oh, but let's push. We're gonna finish it. Minus cos, this one is what? Theta 2 plus M3 GL1 minus cos theta 3. Yeah, my good people, if you have done this like this, believe me, you will not get it wrong. Now what is left to do is apply the Lagrange's formula and solve our equation. How many variables do we have? We have theta 1, theta 2, and theta 3. So now, and I said it in the beginning, guys, if you guys remember in our first session, the number of systems that you have, there is a question. Please ask your question, or is a text. We don't write the subscript of L like L1, L2, because we assume L is the same throughout the system. Yes, my brother, that's it. Thank you. You answered. Yes. That's it, my brother.
I know it's fine. I understand. Thanks.
Now you're welcome.
Thanks.
Yeah. Yeah, it is the same, but you can see from the picture how they are looking. Now, since we've done this, what do we do next year? We apply Lagrange's, and I said you have a system 1, theta 1, system 2, theta 2, system 3, theta 3. Because you have 3 systems, it means you're going to have 3 different equations. It's simple as that. Number of system, number of equations. You have 4 equations. You have 1 equation. You have 2 equations. Now, because we know that we're going to have 3 equations, let's start with the first one. Let's say for theta 1. Let me write like this, theta 1, for theta 1. How will the Lagrange's look? The Lagrange is going to be G in terms of dt partial of G over partial. Now you replace by theta dot of 1, because the main subject here is theta 1, minus partial G partial theta 1. You can see the way I'm writing it, plus partial U over partial theta 1 to be equal to 0. Now that we are writing this, we can start solving. Let me just check, do I still have enough time, or should I send a new link? call end soon. Let's continue. If it's 5 minutes, I will end it and send a new one. We push this. Guys, I hope you are copying, and if you are not copying, no problem. I will take time after my class today to edit, and this video will be on my YouTube channel. Not all the things that we'll be doing in this class will be on my YouTube channel, otherwise it will not help the people who are paying. So this one is free, therefore you will find it on my YouTube channel. So make sure you subscribe for more content. Now here we go, guys. What do we do now? Important thing, guys, you guys have done partial differentiation in math form. Remember, if you have partial let's say of function x in terms of x, let's say your function here, it is x squared plus y squared. What is the answer? In this case, the answer is 2x, because the variable is x, and if the variable is x, it means whoever which is not x is taken as a constant, and differentiation of a constant is 0. Now the most important thing, you can see the guy that is in front of this guy here. This is important, I need to write it here. If you have something where the variable is time, you have to be careful, guys. Be careful. If your variable is time, let's say your function is x, your answer here is going to be x dot. Because is it time, it means it is the displacement, it gives you the velocity. If you differentiate in terms of time, x dot, it gives you x dot dot. So you have displacement, velocity, and acceleration. Why is it like this? Because the variable is time. So pay attention. Same apply with angular. If you have displacement where the variable is time, in terms of angular theta, you will have theta dot. If you differentiate in terms of time, you can see time, the way it's changing the equation of theta dot, it gives you theta dot dot. Now you have the displacement, angular displacement, angular velocity, and angular acceleration. This is the first main important of your solution. You need to know these two. You need to know this partial here, I'm differentiating partially, and now that I'm bringing this in terms of time, now things will change. I will not have expression of x or what, but I will be having now velocities or acceleration. Please pay attention to that. Now in our case here, I'm moving a bit fast. I don't know if I'm too fast, but you guys can get me. If I go partial chi, I'm doing it step by step. Partial theta dot 1. Now let's see what's happening. We are coming to this equation 1 here, the two quotes here. We are differentiating in terms of theta dot 1. What is the method to use, guys? You identify. You look in this expression. Do you have theta 1? No. Do you have theta 1? No. This one is m2l square. No. Because you don't have theta 1 here, this whole expression here, they are acting like a constant, and differentiation of a constant gives me what? 0. Now the only guy that I will be differentiating it is this expression. So you are basically differentiating half m1 l square of theta dot 1 square. But remember, your variable is theta 1, so it means this guys here is still a constant. It's basically like having if you are having 2x square, what is the answer of this differentiation? It's simply gonna be your 2 that you have here in the beginning. You are simply differentiating x because that is the variable. Multiply by what? 2x. Hey, this multiplication look like x, but you get what I'm saying. Multiply by what? 2x. So in this case, what you are having here, you still have your guys half m1 l1 square. What you are differentiating is theta 1 square. So it's going to drop to theta dot, because the 2 is falling. Name the difference. This one is falling because the variable here is theta. The variable is what? Theta. But when it will come to the variable to be time, therefore you will see what will happen. So in this case, I can factorize this expression to cancel this. Therefore, the expression that I have, it is m1 L squared. That is the reason why this answer for this partial derivative here, it is simply m1 L squared. I forgot something. Theta dot. It's supposed to be theta dot here. This is the first step. Am I still in class? I don't think. Time is still here. You guys can hear me. Please stop me if you don't get it. Now, this is the first one. Now, remember, this is not the final answer. It says that now what you are doing, you are differentiating now in terms of time. This is what it means. This expression. m1 L square theta 1 like this. You see what's happening? That's what the formula means. You differentiate this one first in terms of the variable that you have, and then the answer that you get, you differentiate it in terms of time, because now we are differentiating in terms of time. Now what will happen? We're going to have m1 L square. Our variable here is theta 1, so we're going to be theta dot. Remember, I have mentioned it on top here. When your variable is time, your theta dot becomes theta dot. Your theta becomes theta dot. So if you can do this, it means you are done with the first part of the equation. Now, what's happening here? I'm gonna close this link and send a new one. We continue our problem, but before I close, you have 2 minutes to talk to me if you are satisfied or there's somewhere that you don't get. Hello? Please talk to me, guys. Don't make me feel like I'm alone. I'm already alone in my home. If you don't talk to me. Mr. Tolani, is it fine so far?
Yes, it's fine.
Okay.
I can carry on.
Okay, no
Yeah.
problem. Now, since the call will end soon, I'm just closing and sending you link so that we can continue.
Okay.
Sure.